Hey everyone, so today I'm going to be doing a mathematical proof of correctness on a LeetCode algorithm. So the question I'm going to be solving and that I'm going to be doing a mathematical proof of correction on is called the divisor game. And yeah, I'm going to just quickly read out the prompt and then hopefully you can pause and then try out the question for yourself. And then I'm going to tell you what the algorithm is to solve the question. And then afterwards, I'm going to mathematically prove that the algorithm I propose is correct. So this is kind of what we do in our algorithms course. Well, the next level of algorithms course. So in the first level of algorithms course at university, you learn basic algorithms like stacks, heaps, queues, and simple algorithms like binary search, Dijkstra's, Bellman-Ford, all of those, DP, greedy. You just learn all of those algorithms, and then on the next course or the course afterwards, the more advanced course, you prove that certain algorithms are correct. For example, you could prove mathematically that Dijkstra's will always lead to the shortest path. So I think this is a good thought experiment. This is a good way to show how you actually prove one of these algorithms, and this is a easier algorithm to prove. And I'll show you how to think through it and how to actually prove those. So try out this question for yourself. This question is actually tagged annoying. It's a new category in LeetCode, and it's annoying because the solution requires a mathematical proof and or the most optimal solution. You could probably think of the solution without the proof, but the proof just makes it more solid. All right, let's get into it. So, what is this question actually asking? So, this question is they're playing this very nerdy game called the divisor game, where pretty much there's two players playing this game, Alice and Bob. And the first person that always goes is Alice. So, pretty much there's a number n on the chalkboard, and then each player does a turn, and they alternate turns. And they keep on playing this game until one player until a player can no longer make a move. And I'll explain exactly what a move is. So there's pretty much two rules here. So first, as they mentioned, there's a number n on the chalkboard, and each player has to make a turn, right? Where Alice goes first. So let's just put a random number 8, right? And let's say Alice goes first. Alice's move, right? So there's a number 8 on the board. It starts, and then first they need to choose any number x between 0 and 8, and the number that they choose needs to be able to divide 8 evenly, right? And then afterwards, once they pick a number, replace the number on the board, replace the number n on the chalkboard with n minus x. So subtract the number they chose from the current number. So let's just quickly think about this. What are the different options that they can choose? Well, they can't choose 0 because this is not inclusive, but maybe they could choose 1, 2, 3, 4, 5, 6, 7, right? They can't choose 8 because it's also not inclusive of the right bound here. So now we also have to meet this condition that the number they choose needs to be able to divide 8 evenly. So 8 divided by 1, that works because that divides evenly. 2, that works. 3, that doesn't work. 4 works. 5, 6. So the options that they have is pretty much 1, 2, 4, right? They can choose any of these numbers, and once they choose the number, they need to pretend that they choose 4. Then pretty much what they need to replace the number n on the chalkboard with n minus or 8 minus 4, which they'll get 4. And then the next person to go is Bob, right? What are Bob's options? I mean, Bob doesn't have these options. Bob's option is pretty much 1 and 2. So now Bob, let's just say Bob chooses 1, right? Then we replace this by 1. We do 4 minus 1, we get 3, and now it's Alice's turn. And they pretty much keep doing this until no one can make a move. So yeah, what does it mean for someone to make a move? Well, let's look at this example. N equals to 2. Pretend Alice chooses 1. So pretend it starts at 2, right? And it's Alice's turn. If Alice chooses 1, we subtract this and Alice gets 1, right? Now it's Bob's turn. Bob has to choose any number between 0 and 1. Any whole number. And you can see there's no whole number between 0 and 1. So Bob actually doesn't get any moves. So Bob loses. So that's essentially the game. Pause right there. And then actually try to solve this question. Work through the examples and figure out why Alice loses on 3. And why Alice wins on 2. And yeah, take some time to do that real quick. So pretty much what we want to do is they play until a player cannot make a move and then return true if and only if Alice wins the game. And you also have to assume that both players play optimally. That's another thing. So as I mentioned before, they have multiple options. Like if we go all the way back, when it's Alice's turn, they can choose by 1, 2, and 4. That's why this question is also annoying. It's because it's assuming both players can play optimally. So what does that mean? They need to pick the right number so that they have the highest chance of winning or that they're gonna win. And I'll explain that after, but try this question and I'm gonna do a mathematical proof on this question after. So yeah, hopefully you went ahead and did that. I'm gonna tell you the answer right now is only one line. So essentially this is the answer. If n is even, Alice will always win. If n is odd, Alice will always lose, right? So n could be anywhere between 1,000. So if n is even, Alice could always win, no matter what. Alice will always win if they play optimally. If n is odd, Alice will always lose because Bob will play optimally. So what that looks like is n mod 2 equals to 0. So if n is divisible by 2 with no remainder, Alice wins. Right here, run that. See? Okay. That's why this question is kind of annoying. It's like a one line algorithm. And let me just quickly explain. Let's do a mathematical proof on this. Let's just say if n is always even, Alice will always win. Right? And then we could probably prove the converse. Like if n is odd, Alice or Bob will win. But let's say if n is even, Alice will always win. What's like my reasoning for this? Well, we're gonna break this proof down into 2 steps. First, we're gonna say we're gonna be like theorem 1. If n is even, Alice can always. If n is even on Alice's turn, Alice can always make a move, right? If n is even, Alice will always be able to make a move. The move they can always make is choosing 1, right? So Alice could always make a move because they could always choose 1. If n is even and they could always make a move, that means Alice can never lose when on even. So let's just say theorem 1 is can't lose on even. That's what we're going to call it. So if they can't lose on even because they always make a turn, I'm going to prove another theorem. Can force even on next turn. So Alice can always force even on next turn. If they're on even, if they're currently on even, they can always force them to get back on another even. If. So now think about this. If I'm on even and I can never lose when I'm even, because I could always choose one, and I could always force myself to get onto the even, to get even on the next turn, then I can never lose, and that means Bob is gonna lose. Just think about that a bit. So let's prove theorem 1. If n is even on Alice's turn, Alice can always make a move, and the move they can always choose is 1. So you'll see that the constraint here is all n is greater than 1,000, or sorry, or yeah, all n is between 1 and 1,000. So let's go like this. What are all the even numbers between 1 and 1,000? So it has to be 2. It's n is greater than 2. What are all the even numbers greater than 2? 2, 4, 6, 8, 10, 12, right? And like so on. All of these are divisible by 1, because every number is actually divisible by 1. 1 divides every number evenly. Also, if you subtract 1 out of any of these, you still, or basically if you use any of these as the boundary here, it's all, you could always pick a number between 0 and, or you could, or 1 will always be between 0 and any of these numbers. So if we do this, 0, and then we have to choose an x, right? Since 1 can be chosen between here, since 1 is between 0 and 2, and then 2 is less than 4, 4 is less than 6, by transitivity, 1 is also in between 4, 6, 8, 10, etc. So that you could prove that using transitivity. What else? Okay, so that proves the first theorem. If n is Alice can always make a move, but then like okay, Alice can always force even on the next turn. How are they gonna force even on the next turn? I'm gonna say that they're gonna force even on the next turn by choosing 1 every time. So every time Alice has to go, they're gonna choose 1. They do this by choosing 1. Why does that work? Okay. So pretend I'm at an even number, right? So pretty much if I subtract 1 from here, I end up with an odd number, right? If I subtract 1 from an even number, okay, this is what I'm gonna do. 1. If I have an even number, subtract 1 from even number. That leads to an odd number, right? Now Bob has to choose some number that divides. Now Bob has to choose some number that divides an odd number, right? Because now if I choose an odd number, if I choose 1, which is an odd number, I get if I choose 1, which is an odd number, an even minus an odd number equals an odd number. And I can do more proofs on that as well. But since that number is odd now Bob has to choose some number that divides an odd number. And what we'll prove is any odd number, an odd number, let me think about this. An odd number, basically what they need to do is an odd number can only be divided by another odd number. Right? So they need to subtract, so they need to choose an odd number, and odd minus odd is equal to even. So if the current number, if we place it at an odd number, they need to choose an odd number to divide it. And then the next step, right, is to minus that number from x. So odd minus odd is actually equal to an even number. So that's how we can prove it, that we can always get to an even number. Let me move myself here. Yeah, I was blocking it a bit, so that's pretty annoying. Yeah, so what I said is, Alice can always force an even number, right, on the next turn if they're currently an even, and they do this by choosing 1. Once they choose 1, they turn the current number into an odd number, right? Now that it's an odd number, Bob has to choose some number that divides that odd number evenly. Let me write that. Once Bob chooses, and I'll prove this. Once Bob chooses that odd number, or yeah, has to divide an odd number evenly, right? Pretty much only odd numbers can be divided evenly by, like, you need to choose another odd number to divide that odd number evenly, and I'll show the proof for that. And then I'll show that odd minus odd equals to an even number. And then since it's even, that means Alice still has a turn, and Alice lives to fight and play another day. And since Alice will always have a turn, since Alice is pretty much immortal, that means Bob is gonna lose. I hope that all makes sense. This is discrete mathematics. So let's prove this. Let's prove that any odd number. Well, you could already prove that if you subtract 1 from an even number, you get an odd number. What does it mean? What does it mean for a number to be odd? For a number to be even, that means that it can be divisible by 2. So an even number could actually be represented as 2 to the k. Like, what does it mean for something to be divisible? It means, like, if m is divisible by d, that means there's some, let's say this. This is what it means for something to be divisible by d, right? M is divisible. You can divide, m can be divided by d evenly. That means you could find some d multiplied by some q, which is some integer, and that equals m, right? That's what it means for m to be able to be divided by d, right? So what does it mean for something to be even? That means it could be divided by 2, right? That's what even is. So if you represent it like this, like k is any random integer. K is any integer. Has to be integer there. What does it mean for something to be odd? This is how you can represent the odd number, right? Like this is discrete mathematics, right? They tell you this in your first class. So subtract 1 from an even number leads to an odd number. Yeah, because you essentially have this even number, and then you subtract 1 from it, right? That's the form, and then you could prove that you can literally prove that sorry. Yeah. You could prove that this is no longer a multiple of 2, right? You can't factor this so that it leads into this form. So that's why minusing 1 is equal to odd number. Now, let's say Bob has to choose some number that divides. Let's prove this part. Odd number can only be divided evenly by another odd number. Right? So that means odd number can only be divided evenly by another odd number. Let's prove this by contradiction. Assume an even number can divide an odd number. Assume an even number can divide an odd number evenly. Right? that means, say we have this odd number. Say that we have this odd number, and we have this odd number m, right? And then we say that there's some d times q, right? And we're assuming that d is an even number. So let's replace that with the form. So m equals 2 to the k. So we're saying it's some random even number. And then if you simplify that, so if we simplify that, m equals 2kq. Since k and q are both integers, two integers multiplied by each other equals another integer. But essentially, now it's in the form of an even number. So if we're assuming m is odd, and you could find an even number, this is a contradiction. Odd cannot be represented as a factor of 2, right? That's only even. So by contradiction, since we can't choose an even, we have to choose an odd number to divide it. And every number is divisible, right? Even prime numbers are divisible by 1 in itself. So every number is every integer is either odd or even. So if it can't be even, then it has to be odd. So that's the proof. Now that we proved that it can be an odd number, now let's prove the last part. Odd minus odd equals even, and then that kind of finishes our whole thing. So as I mentioned, odd minus odd is equal to even. So what's odd minus odd? What's an odd number? 2k plus 1 minus 2k plus 1, right? Now let's simplify that and let's see if it turns into an even number, right? And we know an even number is 2. Anything like 2, anything that's a factor of 2. So let's simplify this a bit. 2k plus 1 minus 2k minus 1, right? These kind of cancel out, and then we get 2k minus 2k. Oh, sorry. Why am I doing a here? Like L here. Because these are random. Because these could be two different numbers. Right? And then now we have it in this form. And now we pull out the 2. And we get k minus L. Right? That's of the form here. 2 to the... Oh, let's get confusing. Let's just do j. Where j is like a random integer. An integer minus an integer is another integer. So this is actually a factor of 2. So you can see that odd minus odd, when you simplify two odd numbers, you get an even number. And that proves our step 4 here. So yeah, and then so pretty much that's how you would prove out these two theorems and prove that if n is even, Alice will always win. Right? What about if n is odd, right? If n is odd, like if always win, right? Let's do if n is odd. Let's think about this. If n is odd, then essentially Alice, as I mentioned before, if n is odd, Alice has to choose an odd number that can divide that number evenly. So that means Bob will start at even. Since Bob is the one that starts at even first, they'll hit even, and then they can make it so that they can never lose, and then they could always make it so that they get it even on the next turn. Let me know if that makes sense. I hope that's how you solve this question, or how you prove that the correctness of this algorithm. I hope that makes sense. I'll see y'all in the next video.